All right, welcome back, everybody. Before I introduce our next speaker, let me remind you that after this talk, there will be a lunch break, and there will be catering stations all over the place here. So you can find them also in the plan you have in the program. So please don't all run to the next catering station in front of this room, because then we have a huge queue. Yeah, there's a lot of them also on the ground floor and one floor up, so just for your information. But now, as a former cosmologist myself and a current software developer, I am very excited to introduce our next speaker, Daniel Grün. Daniel Grün is a professor for astrophysics, cosmology, and artificial intelligence at LMU. Before that, he held an Einstein Fellowship and a Panofsky Fellowship at Stanford University to lead a research group there. And his research brings together the biggest images from and latest images from the late night sky with analytical models, statistics, and machine learning to study the large-scale structure of the universe. He uses galaxies and gravitational lensing to develop AI-based tools that help researchers to extract valuable and reliable cosmological information from huge and vast, complicated cosmological data sets. So please, welcome Daniel Grün.
Thanks so much, Till. It's a great pleasure to be here and to have been invited to give this talk. For me to be here is only possible because, as you know, the state of Bavaria decided to create 1,000 additional professorships in tech, which is crazy, it's insane, a couple of years ago. And then LMU decided that they were going to see AI not as one additional thing, but as part of their DNA, and that AI was going to be in every subject. And so I'm the person representing AI in the subject of physics and fundamental physics, but you'll find that all over the place. So we're talking about cosmology, which is the physical description of the universe as a whole, and how that may connect to techniques that you know in many other contexts. So I want to give you first some sense of scale of what we're talking about. Whether you're a physicist or not, the universe is probably larger than most of the things that you usually deal with. But it's not unimaginably large. In fact, looking at this picture, you can kind of imagine it. So this picture is humanity's furthest away selfie ever taken. This is from the Voyager probe, and then flying out, almost traversing our solar system, and then one last time turning around and taking a picture. And so you don't see much in that picture, because even our solar system is rather empty, but you see this one little, okay, so that cursor is somewhere else, you get it here. You see one little dot here, okay? So Carl Sagan would say, looks like a speck of dust suspended in a sunbeam, right? So that poetic picture, our Earth looking like just a speck of dust, will help you. I'm going to do something like the Planetenweg, but the Planetenweg doesn't do it. We have to have a pretty extreme model in which, indeed, our planet Earth is a grain of dust, and it's a small grain of dust, the kind of grain of dust that gets in your lungs when you cut a piece of stone or something like that. So a micrometer-sized grain of dust. Imagine that's our planet Earth. And I think you can kind of imagine it. You can breathe it, and you can travel planet Earth. So you can imagine that model. Now, in that model, the entire solar system, which I'm just taking to mean this is as far as Voyager has traveled, would be about the size of a human body. So you can think of our solar system as the size of a human body and a bunch of tiny dust grains flying inside it. That's the planets. But that's not a scale that I'm interested in yet. That's very classic. You could take one further step out. You could actually fit an entire galaxy, like our Milky Way galaxy. This is our neighbor, the Triangulum galaxy, roughly inside the volume of planet Earth. So in the galaxy, you'll find billions of stars and solar systems around them the size of human beings, with these tiny dust grains the size of planets. That's not yet the scale that I'm interested in. The first scale that I'm kind of interested in is the scale of clusters of galaxies. So here what you see is a bunch of these fuzzy blobs. Each fuzzy blob is a galaxy of its own, roughly the size of our Milky Way, some larger, some smaller than that. And that would actually fit in the volume between the moon and the Earth. So you can see that actually galaxies are kind of placed close together. You have these relatively large things, relatively densely packed in a galaxy cluster, and that's what makes them interesting from the perspective of a cosmologist. But you can take one more step out, and now you can actually imagine the size of the entire observable universe. The size of the entire observable universe in this model is about the size of our solar system that Voyager has traveled. Okay? So this is what I'm asking you to do to overcome this notion that the universe is unimaginably large. I'm asking you to imagine, which I propose you can, Earth as a grain of dust. Then the entire universe will fit in the solar system, which is something we can actually travel, at least in the span of decades now. So how does that entire solar system work? How does that entire universe work that fits in the solar system? That's the question that I'm trying to answer. Now, what is there even to say about the universe as a whole? I would contend there's actually kind of only one diagram that you need to be able to make and to understand, and it's this diagram. So this diagram shows you what is the size the universe had as a function of its age. I put some things into that. I tell you that, well, the universe has an age. There was a time in the past where it started. And I told you that the size of the universe is actually changing. And those two things are related. We've known for almost 100 years now that everything is moving away from us on the scale of galaxies. The universe is expanding. So if you turn that around, everything will have to have been closer together in the past. In fact, at some point in the past, everything was just in the same place. And that determines the age of the universe. Now, usually what you would expect the universe to do is the same that you would expect if you throw a ball. Okay, so this is kind of the curve that a ball would leave in this room if I throw it to the back. It starts going up, and then it goes up slower, 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 and eventually you'd imagine that it may fall back down. Right? Gravity attracts the ball to everything else in the universe. And so we think this is what the universe has been doing for most of its time, but it's not the whole story. We think the universe actually had two periods where the opposite was true. We think that at its very beginning, the universe started out in an accelerated exponential expansion for a very tiny period of time, but we need that phase to explain some of its properties. And then we think, which is maybe even more surprising, that not so long ago, a couple billion years ago, the universe decided to again enter a phase of exponential expansion. So that's the blue block in this diagram. So how we find out that that is indeed what that curve should look like and then explain it physically, that is what cosmology is about. Now, the good news is that while you can kind of only make that one diagram, there's a sense in which you have more than one universe. And this is the beauty of physics. If you found a law that applies to everything, that same law will apply to every piece of it, but it will have different consequences because all the pieces are different in their initial conditions. So we think that if you look at any piece of the universe, it will behave just like a universe of its own, but with a different density, because the density in the universe is different in each place. And so this structure, this different density in different places, we think comes from that very early period. It comes from quantum fluctuations in that early exponential period, which I'm drawing some kind of funny wave here. All that means is you can't have the same density everywhere because of quantum fluctuations. And these got inflated to variations in density that are the seed of all the structure, all the inhomogeneity, including us in this room, that are in the universe today. So we can see traces of that in what's called the cosmic microwave background. This is thermal radiation. You measure the temperature in the sky, and the radiation you receive is from when the universe was just 380,000 years old. Okay? So back then, the universe was filled with plasma, and there were tiny differences in the temperature of that plasma because of those density differences that we can still record very clearly today. So that's the red and blue soup here. Oops, where's my cursor? I don't know where my cursor is. Oops, there we go. And then for most of its time, gravity had a great party. gravitational attraction was growing whatever was big, even bigger. It was attracting more material. So stars could form, galaxies could form, clusters of galaxies could form, subsequently over time, ever bigger things as the universe grows older. So I have a question for you, which is a question I'll always ask in my astrophysics or cosmology 101 exam, okay, which you're welcome to come to LMU and take it, but I'll ask you here, what happens lately when the universe is again entering this accelerated exponential expansion? What happens to clusters of galaxies? Are they growing still? Are they growing faster or more slowly? So we're going to do a rock, paper, scissors here, right? I'm going to give you your options, rock, paper, scissors. I'm going to ask you all to raise your hand, and then we'll see whether you pass. So, one option is right now, as this expansion is getting faster, that will mean that also structures will grow even faster than they had in the past. So, the galaxies are going to get bigger, the clusters of galaxies are going to get bigger even faster. That would be rock. If you think the opposite is true, if you think that this accelerated expansion of the universe, it will lead to growth being more difficult. It will lead to big things just remaining the size that they are now in terms of the mass that they contain now. That will be paper. Right? And then if you think that this is a separate problem, that while this accelerated expansion is happening to the universe as a whole, it doesn't actually happen to the structures inside of it. We don't care. Then that will be scissors. So I give you a second to think. I'm going to count to 3. I'm going to ask you to raise your hand, and those who say the right thing, they're going to get a certificate later or something. I don't know. Whatever you hand me, I'm going to sign it. So we're going to count to 3. You're going to raise your hand. Rock, paper, scissors. So 1, 2, 3. All right. Some diversity in your answers, but a lot of people got it. So the answer is that indeed the growth of structure is going to slow down. Everything is moving apart from everything, and that process is accelerating. So it's going to be very difficult to accrete more stuff. In fact, if this expansion is happening the simplest way that we think, in an exponential way, we'll be very lonely pretty soon. This is a good time to study other galaxies because we won't see them in the future. They'll be outside our horizon. So we think that structure should be in the process of stopping to grow if indeed the universe is exponentially expanding soon. Right. So this is the two ways. You could tell the story of the universe by looking at it as a whole. You could look at the structures inside of it. Hopefully you would find the same story, the same laws of physics describe all of that. Then you should consider yourself lucky. So how do we do that? Right? And the laws of physics that so far best describe all these observations, they're actually very simple. This curve, while it looks somewhat arbitrary, it kind of just says all the stuff that you could imagine is present in the universe at some manufactured density that we need to make this exact curve happen. And in order to do that, we need matter. We need usual matter. But actually, we need a lot more than the usual matter that we find is present, the matter that you and I are made of. So, okay, we'll add some matter. We don't know what it is. We'll call it dark matter because we don't see it. But it's doing gravity, and we need it to describe this curve and the growth of structure. And then for this speeding up to happen, matter can't do that. Matter does positive gravity. Everything attracts everything. We need something else. Now, the simplest something else that does that is if you just fill vacuum with a constant energy density. At some point, the matter is so diluted because the universe has expanded enough that this constant energy density actually is the most energy that's left in the universe. And a constant energy density, plug it in Einstein's equations, is going to cause an accelerated expansion. Okay. So we just made these up. These are the simplest things that we can make up to describe the observations of this curve and structure that we've made. But what they are is really not answered. We're really begging the question here, in a sense, of what the physical laws of the universe are. We need to find out, and we can only find out if we find any small differences between what these simple things predict and between what we measure. That would tell us that maybe dark matter isn't entirely dark, maybe dark energy isn't actually a cosmological, it's not actually a vacuum energy density, but is a little different from that. And then we can have some hope of finding it in an expanded model of fundamental physics. It's not explained by our standard model of particle physics at all. All right. So what does AI do here, right? So how does AI fit into this? I want to contrast it with kind of a textbook AI problem. Actually, surprisingly difficult enough AI problem, but you could try to design an AI that tells you which of these pictures shows a cat and which of these pictures shows a dog. Right? We've gotten rather good at that. You would feed some labeled pictures maybe, or maybe you would do something smarter and minimize some kind of cost function to tell you which is a cat, which is a dog, and it'll work most of the time. Now, no single piece of the universe can give you the answer in cosmology. And no single piece of the universe is observable well enough to actually tell what it is. Right? So we're more in this situation where everything is blurry. And fortunately, we're though in the situation that the universe is rather large, as I told you. So we can collect a huge amount of data. No single bit of it tells us particularly much. But when we put it all together, we can ask questions like, is this exactly an equal mix of cats and dogs? Is the accelerated expansion of the universe caused exactly by a vacuum energy density? Is dark matter exactly dark and cold and collisionless? Or is there a small deviation that tells us what the nature is? And probably 10,000 cats and dogs aren't even enough. Maybe we need 1 million of them. Maybe we need even more. And so this is the context in which we're looking for AI to support our research. And I'll tell you about, I would say, 3 themes, 3 types of ways in which AI can support cosmological research and reasoning. And this is it, right? I think there's a big data making it efficient to even just do the processing. There's being both precise and accurate, and I'll tell you what I mean by that. And then there's also a way in which we have reached the limits of just human labor in analyzing this data carefully and what that means for us. So let's start with, the bigness of our data and what that means for AI. So I think this is actually a uniquely, crazy situation in the volume of data that we're able to collect, and I'll tell you why. There are 2 things that are growing rapidly. One thing that is growing rapidly that you may be less aware of from the IT perspective is that telescopes are growing rapidly. Okay, telescopes, 100 years ago were kind of crap. Okay, so at LMU's observatory, we have what at the time was world's most powerful telescope, and you can buy something like that from pocket money today. We are getting better and increasingly so at building big telescopes that take very sharp images, and they do it over large sky areas. And we're also multiplying those telescopes. We're deploying more and more of them. And that just increases our ability in collecting light that comes from the sky and from these distant objects. But you have to multiply this optical and mechanical progress with the progress of silicon technology, right? How do you record those photons? That's the second thing that you need to do. So, 1836, we had a person looking through an eyepiece and, making sketches with a pen on paper. There wasn't even, photography was not feasible in this regard. Whereas these days, astronomers are deploying the largest digital cameras in existence on these telescopes to take fast images over large sky areas repeatedly. Okay, so this is the very latest version of it. This is a camera that we're deploying on a 6.5 meter telescope in Chile that's going to survey the entire sky visible from Chile every 3 nights. It's the largest digital camera in existence. And then when you want to collect the light of individual galaxies and you want to turn it into a rainbow, a spectrum, and measure the details of it, we now have instruments that can do that simultaneously for 5,000 galaxies by robotically positioning a little fiber to collect the light of just that galaxy, right? So a couple years ago, it was 1, now it's 5,000. So the silicon technology is kind of Moore's law, and it multiplies with our optical and mechanical technology, and that leads to just a flood of data that you kind of can't even keep up with just silicon technology. You also have to look for new algorithms. Right? So LSST is going to collect 500 petabytes, and we want to process that all very precisely and accurately. So one such area in which we need AI is that if you have big data sets and you want to ask the questions, is this data as I expect it to be in my model of physics, then you first need to simulate in your model of physics what that data should look like over the same volume that you have observed with your telescope, but for many different models for what you think the physics might be. Okay, so you need a multiple of the volume that you observe simulated. Now, we know how to do that in the simpler models, at least. It's just gravity. You put particles in a box, and you let them gravitate with each other. But it is a lot of computation that you have to do. So the latest simulated universe data sets, they use of order 100 million CPU hours to generate. Right? So at some point, that becomes infeasible. You keep super Moore increasing the volume, and maybe you also get interested in a greater variety of physical models, then you just hit a wall. So instead, what you could imagine doing is you could imagine leaving this generation of synthetic universes to a machine. Okay, so this is an example, a simple example. Jet Homer, postdoc in my group, has trained a generative model on a small subset, maybe a smaller volume of these simulations that have taken millions of CPU hours to generate, to spit out a new rendition of the universe in a second. Right? So on one of these sides, you see millions of CPU hours, and on the other side, you see a minute of generating synthetic universes from scratch. Now, you could do the raise your hand, which is which. You're kind of staring at it. Can you tell? And the answer is that these techniques have gotten good enough at being statistically indistinguishable from actually spending the millions of CPU hours, right? So this is actually generated by AI, right? You couldn't tell the difference. But it's not just you can't tell the real cat from the fake cat. You can't tell with any statistical method that we can come up with the real universe or the truly simulated universe from the generated universe. Second area that I want to tell you about is that AI is not just about volume, but it's also about being very constraining, being precise and accurate in the statements that we can draw from the data that we're collecting. So one technique that I use a lot in my research, and I just want to give you a sense of what that technique is about, and maybe over lunch you'll have a suitable glass and you make a stain of red wine. I don't know whether you're having that. That's kind of what it does, right? So when you look at the background world through the bottom of a wine glass, you see a distorted picture. In fact, you might see something that looks sort of banana-shaped, where there's really a circular spot. That's optics, simple optics. But the same simple optics actually happen in the sky. So there's this galaxy cluster, which I've shown you on my title slide. It's sitting here. And if you look closely around that galaxy cluster, you also see these kind of banana-shaped things. That's not what they really look like. These banana-shaped things, they're galaxies in the background of the cluster. They're truly actually closer to the line of sight of the cluster, and they're smaller in reality, and they're, on average, round. But the deflection of the light rays that they send to us in the tidal gravitational field of that foreground mass concentration leads us to think they look like bananas a little further out and a little expanded and magnified. So this effect is called gravitational lensing. It's just like optical lensing. And it's useful because it's the most direct connection that we can make to the dark matter. The distortion of these images is due to the underlying matter density, most of which is in the form of dark matter. And so if you're able to measure the tangential shapes. If you measure the degree to which galaxies appear tangentially aligned around a place in the sky, that tangential shear, here in red, is actually equal to the matter density inside that circle minus the matter density on the edge of that circle. So that's what the kappa minus kappa here is. And kappa really is just really the matter density, sigma, so it's kilograms per square meter of sightline, and then normalized in some way that has to do with the distances. Same as if you were doing an optics experiment, you need to know what are the distances between the light source and the lens and so on, right? So in order to learn something, you need to be able to measure the shapes of galaxies to see how aligned they are, and you need to know the distances of those galaxies, or at least the distribution of distances of those galaxies, very accurately. That means you can't get it wrong by even 1% if you don't want to be limited by that. So how can we actually tell, right? In this image that I'm showing you, almost everything except that annoying red star is a faint background galaxy whose shape and distance I want to estimate. But from the image, it's not at all apparent what you would do. Here's the strategy that we're pursuing, right? So our current, what I think is our best bet for the next generation is we need to conduct wide area of the sky and very deep, so going to very faint galaxies, very precisely observed observations. We need to very precisely characterize the observational effects. So we need to know our telescope, very closely. We need to know our algorithms that process the images very closely. In fact, we have to simulate that, and in fact, we have to emulate that because it would take too much time to simulate that at the volume. And then what we're planning to do here, and what we've started on doing, is to train something that you could call a foundation model for galaxies. So given the different modalities of data we can collect on galaxies, and the noise that they have, and the selection effects that they have, can we train a model that tells us, here's the true population of galaxies, and what are all the observational properties that could come from it, and what happens if you take an image like that and you measure for some subset the shapes, what is the distribution of distances that those galaxies have. So this is a joint project across 8 universities in Germany, supported by BMFTR, for us to do that over the coming 3 years. We've already done data collection, so up here you actually see a self-organizing map that spreads out over the color space of galaxies. So every pixel in this map is a color that we can distinguish in our images, and then I'm coloring that pixel by what is the mean distance or the median distance of galaxies that we have determined with very expensive spectroscopic observations. So this is an area in which we're working. There's another way, and this was mostly about what I call accurate. So we don't want to get the answer wrong by even 1%. There's also precise, which is we want to make a statement that is as narrowing down the physics as possible from the data that we've collected. And so this is how this could work, right? So you could imagine that you've collected some data. Maybe it's a map of this gravitational lensing signal over some large area of the sky. So that's what maybe that map looks like. Maybe you've collected a bunch of different maps. And then you could imagine processing these maps with a convolutional neural network or something to eventually provide estimates of the physical parameters that you care about. Properties of our universe. What's the matter density of our universe? What are the properties of this accelerating expansion? Including their uncertainties, actually. We care about how certain we are on that answer just as much as we care about the answer. So we're doing this, for instance, for a type of data called the Lyman alpha forest spectra. We're taking particular spectra in which we can see hydrogen gas clouds because when the hydrogen is still neutral, they absorb the Lyman alpha wavelength of light. And we can kind of see a dip in the spectrum wherever we hit a cloud along the line of sight to a background light source. Anyway, it doesn't matter. There's some data that we collect that's sort of difficult to analytically deal with. I'm mentioning 2 students here who recently graduated who did the work that I'm showing you on the next slide. So we could apply all the human ways of analyzing that data, right? So there's 4 different ones. You don't need to know what these letters mean, but these are things that people have done in the past, given such data, to infer something about two parameters of interest that, it doesn't even matter what they are. But this is what usually this problem is like in cosmology. How small a circle can we make on this diagram such that we're sure the truth is somewhere inside it? Here we know the truth because we're simulating it. That's the crosshair. So all these different ways that we could analyze our data with human-made methods, they give us different contours, different areas on this diagram where we think the truth is somewhere inside there. Now, when Parth and Sukyam did this with a kind of architecture that I just shown you, they got this. Okay, so when you say, I'm not going to decide what features I'm looking at, I'm not going to look at the two-point correlation or the PDF or whatever choice you may make of the data, but I'm just going to feed the entire data to my neural network and let it predict the answer. I'm going to train that on simulations, and I'm going to see how well that does on new simulations that I'm getting. It's doing this well. So we've called it human versus machine 1, 2, 3, because at the time, that still seemed like a good outcome for the machine. I think the score has changed over the past year quite a bit. And it comes from combining all the human ways that have been applied to this statistic. You're still 3 times more uncertain about the physics answer than the machine is from just looking at the spectrum and just brute force training it. So this way of extracting information that we as humans haven't found a way of the course of human history to extract from the data is very powerful in this area. Good. And then one version of this is also that machines can serve as more complex models for astrophysical phenomena than we would be able to do analytically. So what you see here is again from a simulation by JED. Here's some kind of density field. So it's similar to maybe we could measure such a map using gravitational lensing of the density in the sky. And then what Jet has done is he's trained a generative model to kind of, from a random number, produce such density fields, and he's developed a technique by which he can sample this efficiently. So you can imagine you're going to sample from this sort of noise space until you find a map, which is just around now, that looks comparable, it looks consistent with the map that you've actually measured. And so this way you could constrain the physics parameters that go into your generative model using the full information that's in the data that you've collected. So this is one idea in which we can make use of the beautiful depth and diversity of the data that we're able to collect by having models trained on simulations that need to be very good, that can actually reproduce them fully. All right. I go to the kind of final area, and this is, I think, the most in flux, I would say. The first 2 are pretty well established, and I'm actually curious in chatting to you later, how you're thinking about that in your field. I have a very limited, very special view of this that's in my field that I want to present to you. And this is how humans and machines interact in actually doing research. So here's a plot that I love, made by my colleague Eric Huff from JPL. So Eric, at the time, is a couple of years old, had gone through the literature and had done 2 things. So he had taken from the literature what is the uncertainty that people think they have on one parameter that we're trying to measure, the power spectrum amplitude. That's basically how clumpy the universe is. Okay, so this is how uncertain we are on that clumpiness. The oldest study is over here, we're 10% uncertain. The newer studies are here, we're 3% uncertain. And actually these days we're kind of 1% uncertain, because it's been a few years since Eric made that plot. And so Eric has tried to see how much work that was. It's difficult. In science we work in collaborations where people work together somewhat more informally than in a business context usually. But you can kind of tell how many people are on that collaboration, what fraction of their time are they likely spending on that project, how long did it take from when they collected the data to when they published a result. You can guesstimate just how many years of human labor it took to do that. Right, so we started with studies that kind of a graduate student could do. So this is a couple, this is maybe 20 years. You have a graduate student, you have a postdoc. You can almost do it with a research group, right? And we've moved to studies that take like 100-person years. So you need a sizable team, and maybe you need a couple of years. And we're probably at the stage where we take like 300, 400-person years to do the next analysis in this area. But of course, our goals, we've actually got funded. We're very lucky to have instruments that would allow us, over the next 5 to 10 years, to conduct experiments that are, they're only kind of 2 per mil uncertainty on this quantity. We're collecting more data, and that abundance of data allows us to be more constraining, have a smaller error. That's the whole point. So if you just extrapolate that curve, then you end up requiring thousands of years of human labor to do that well. So if we keep going in the same mode, of course Eric has fitted it and is finding that the effort is proportional to 1 over the error, and then it's a bit worse than that, right? So if we do 10 times better on the error, we need more than 10 times the labor. So I think that's just unfeasible. We don't actually have funding to pay those scientists, but we also don't have those scientists, right? There's not enough people who do this or who should do this, right? So I think the next generation of these experiments, if we kept going like we were, they might just exceed the plausible workforce that we have in this area. So, how about agentic AI, right? So this is a development in our field that I think people mostly kind of were smiling and laughing over 2 years ago. It was kind of a toy game, but it has actually become quite common, and people who are effective are using this effectively to automate large parts of research, particularly theoretical research, but also data analysis research. Not so many of us are able to automate their instrumentation-related research yet, but you can automate large parts of cosmological research. I have recently been to a colloquium where, while the colloquium was being given, in the background, a paper on theoretical cosmology was being written by an agent with kind of a page of input of ideas. This is possible now, and it's likely that the possibilities will increase in the near future. Now, I'll start by saying where this is unambiguously great. Even at the level of requiring only a few hundred years of human labor, we don't usually repeat experiments. We collect the data once, and then we struggle to analyze it well. And so, it's really important for scientific insights that you can come up to the same conclusion again, but we just don't have the resources. So there is a movement of making scientific analyses reproducible by agents that I think is very commendable, because it bridges that gap. It makes it affordable to do something again, and maybe also to question some of the assumptions that were made in that process. But there is another big discussion, which is, what does that mean for our field? What does that mean for who we are as scientists? And what does that mean, I think, for the education of scientists? So I'm just highlighting 2 contributions to that discussion that kind of made waves in my community. David Hawk here, a colleague from New York University, kind of going back and asking, why are we even doing this? And concluding that perhaps, if we automate all of research and we're faster at generating insight, perhaps we're actually still losing most of what the reasons were that we were doing it in the first place. And then Hiranya Paris here from Cambridge, arguing that, well, maybe this is a sign that just what it means to be a scientist and what it means to be doing good science is shifting. Maybe that's just a sign that science has kind of gone into the wrong direction by specializing people on technical tasks. We need people who have broader level critical thinking, so they can interact with the specialized technical tasks that agents can do really well effectively. Right? So there's a very rapid change in what it means to be a scientist. And yeah, I'm really curious to find how you're thinking about this from an IT perspective. Right. I'll summarize here. So I told you about what I would call maybe not just cosmological challenges, but cosmological collaboration with artificial intelligence. We have this challenge of measuring small signals, and we don't even know what they look like, in big data that would tell us what is wrong about our very arbitrary, pulled out of a hat model of dark energy and dark matter, governing the universe. Artificial intelligence is crucial in this because it's the only way to enable analyses that take a lot of compute, but that can be emulated. It can be a tool to be precise, so to extract as much information as possible, but also to be accurate, to have models of the complicated systematics and astrophysics that affect our measurement, that go beyond the simple prescriptions that human researchers could write down. And artificial intelligence is definitely in the process of changing the entire workflow of scientific research and science education. So yeah, it's for these reasons that future cosmological analyses will be impossible without AI being a collaborator on these multiple fronts. And I'm looking forward to discussing more with you about that. Thank you.
Yeah, thank you, Daniel. Are there any questions?
Hi, thank you. So some of the techniques and the methodologies that you presented today are things that I have also recognized in, like, from the past, basically. So, and not to belittle the research still, it's wonderful. How much do you think has the recent advances in this field been driven by advances in technology, advances in AI, and how much is through increased awareness and thereby availability of funding for these sorts of projects?
So I'm taking your question to mean, well, progress hasn't been as fast as you were hoping maybe over the past 20 years, and I think that's true. I share that. This picture of cosmology that I've just presented to you is 25 years old, one could argue, right? This is how long our best understanding of the cosmos is kind of what I told you, dark matter, dark energy, we don't know what they are, but it roughly fits. So, I think in a sense, this was so unexpected and so challenging to answer that we needed a generation of both experiments and personnel to even just prepare to answer it. And that is what we call the stage 3 experiments that I've shown you some plots and results from. The dark energy survey, but the kilodegree survey and others. So, these, in a sense, 20 years ago were planned to be a bridge to where we needed to be to actually answer the question. So we now have a much greater and much more specialized workforce, and we have much more technological experience. And the experiments that we have, sincere hope to answer these questions are just around now starting. I don't think we're entirely prepared for what is now starting, this flood of data, and I've shown you some reasons why. I'm hopeful that AI can contribute. But it's a combination of technology and human understanding that we had to build that now puts us in a place where I'm hopeful, by the time I retire, we have answers that are actually satisfying on what dark energy and dark matter are.
I have one question on the foundational model, the cosmological foundational model, because it sounds like a big thing. Do you have an estimate of how many parameters it will have or has?
I would say compared to human language, galaxies are still actually rather simple. So it's not terrible. There are foundation models now beginning to kind of enter the discussion. Aeon is one that's been trained and that has some utility. So I think it's not so much about the number of parameters. It's actually not so much about very precisely predicting every detailed aspect of a galaxy. What is interesting, I think, in this project is that we care about the statistics of it. We care about the overall description of this ensemble of galaxies to be very accurate, to be very precisely close to the overall ensemble of galaxies that are out in the universe. So it's a bit of a additional demand that we have, but I don't think it's primarily a demand that you need a huge number of parameters for.
Hi, thanks for the interesting talk. One part that caught my attention was that your generative model is statistically indistinguishable with the training set or simulated one. That means your generative model is aware of the invariance that the universe has to satisfy, time invariant or spatial invariant and so on. Are these emergent properties, or do you embed those properties into your training?
Both approaches exist. Some people think that it is important to embed symmetries in the training. It is not so difficult to do it, right? You could even just say, I'm going to take anything I generate and I'm also going to rotate it, and that's another universe for you, right? For the case of isotropy. Other people would argue that, just given enough data, you should not worry about this. And I think these are two strategies currently followed in parallel by different parts of the community. I'm more of a fan of using the simple symmetries and actually building them, and I think that's where we gain substantially.
Hi, I loved the talk. And also, when you asked the question, I think the shift in IT is quite similar, where you just have less of the, tedious work and more like the big picture work is coming up. You in one of your sites, when you showed the papers, you said that also papers are now basically, you start with a page and then AI writes the paper, and I think that sounds a bit horrible. I know, it's a bit like when I write an email, I have bullet points, that I write the email, and then the other person doesn't want to read the email and abstracts it back to bullet points.
Yeah.
And that sounds like a very horrible workflow, basically.
Yeah, I mean, I'm not sure what to say of that. So I'm genuinely curious whether people in IT are as scared out of their mind about it as many people in my community are. Because they say, all I do is no longer a thing, right? So, writing a paper used to have multiple purposes. Writing a paper used to have the purpose of teaching a student who's actually writing the paper, critical working and thinking. It had the purpose of clarifying something for your own mind by wondering what was a good question and how to present the answer. And I think there is a huge loss in automating that entire process, which I think we are beginning to be able to do. So Denario, I mean, they actually did the experiment and kind of generated theoretical cosmology papers that they then submitted to experts to evaluate, and some of those papers would just be accepted in kind of leading journals. I assume that is happening all the time, because what journal editors are telling me is that they're completely flooded. Okay, so I think what is definitely true is that the way that science used to work until last year is hitting a wall. Right? That's not how we can continue. Because it's this small incremental sort of progress that you make in the form of a paper that an agent can write in 20 minutes. That's not, you can't you can't evaluate people based on how many times they did that. You can't educate people by watching the agent do that. So you have to find new ways of at least educating people and then evaluating the work they do. And probably we have to think differently about what is a meaningful piece of work.
All right, I think we have time for one more question. So,
I'm on the board of Springer Nature, the publisher of Nature magazine, and we have a lot of discussion about what the implications of this are. Do you foresee a scenario where authorship will shift to a model that a paper will not be published by a human author or by a group of authors, but by a multi-agent system?
Asking me to make a prediction about the future. I'm scientifically trained to include my uncertainty in any prediction that I make about the future. So I'm uncertain. But to me, authorship is more than having done the writing. Authorship is taking the responsibility. Right? So in my field, if you publish a paper and it's wrong, that's really bad. That reflects very poorly on you. There is a sense in which I'm responsible for the things I put out because they have an impact. If I put out something that is just false for reasons that I should have seen, that could cost people decades of labor to unravel. So I think that responsibility needs to remain with a human. That's my personal understanding. There's some things that are, I think, just there's an ethics of who can be responsible, and I think that needs to remain a human, certainly in this area. But at the same time, I think that responsibility could be coupled to things like, while a human wrote this paper, it comes with instructions for an agent that can reproduce the research. So there is a sense in which maybe you're making transparent that an agent did the actual stuff, and you're making transparent how, but there's still a human who signs that with their name and says, I'm responsible, and if we did something stupid, you can hold me accountable.
all right, thank you. I'm sorry, I have to cut off this very interesting discussion now, but let's thank Daniel again for this really, really interesting and nice talk. And thank you to all of you for the nice questions.